Welcome to the summary lesson entitled Confidence Intervals for the Impatient. I say it's for the impatient because this will be a quick overview. You may find this lesson helpful after you've seen a few confidence intervals and need a little help in getting things sorted out about when you use which formula. The discussion here will be limited to those problems that involve only one mean or one proportion. For the case of one mean, we'll be looking at the case where either you do or do not know the standard deviation of the population. So that you know where we're going to be doing three different problems here. The very first problem is a problem involving one mean where the standard deviation is known. The second problem is going to involve one proportion. Finally, we're going to do a problem once again with one mean, but here the standard deviation of the population is unknown. So let's jump right into these. Our first problem says that a random sample of 10 adult male bobcats has been taken. The mean weight of the sample is 19.7 pounds. From long experience with this population, we believe the standard deviation of the population is 2.4 pounds. We want 95 and 99% confidence intervals for the mean weight of all adult bobcats in this population. Now, when we're trying to work efficiently, the first thing we want to do is summarize the information that we have. Sample size is 10, sample mean 19.7, population standard deviation is 2.4. We need 95 and 99% confidence intervals. The formula for confidence intervals is always this. Or at least, it's always this when what we know is the sample mean, the sample size, and the population standard deviation. The difference between the 95 and the 99% confidence intervals is going to come in right here when we compute the critical z-value.
So let's look up the critical values that we'll be needing. At 95% confidence, the critical value is 1.96. At 99% confidence, the critical value is 2.58. All right, then we have our data. We know what we're trying to compute. We have our critical values. We're ready to go. We'll begin with the 95% confidence interval. The formula we're going to work with is right here. The sample mean plus or minus the critical value times the population standard deviation divided by the square root of the sample size. X bar is 19.7. We add and subtract the 95% critical value, which is 1.96. Then we multiply by the standard deviation of the population and divide by the square root of the sample size. We are ready to start calculating. 19.7 is the sample mean or the point estimate. The part that we add and subtract is called the margin of error. Let's compute that first. All we need to do now is to both add and subtract this margin of error from the point estimate. There is our 95% confidence interval for the mean of the population. In other words, we believe that the mean of the whole population lies somewhere between 18.21 pounds and 21.19 pounds. Another way of summarizing would be to say this. Our one number best guess for the average weight of these bobcats is 19.7 pounds. If you ask us, how close do we think we are to the true value, we'd say we don't think the error is any more than 1.49 pounds. How confident are we in those statements? Well, we're 95% confident. Now, our original instructions said to find both 95 and 99% confidence intervals, so we need to repeat this at the 99% confidence level. really everything in our calculation is going to stay the same with one exception. The Z critical value depends on the level of confidence. For 95%, the Z critical value is 1.96. For 99%, it's 2.58. And as you recall, we have a table where we can look that kind of information up when we need it. Now I've typed these values into my calculator, and I find out that this margin of error is equal to 1.958, and then I can both add and subtract the margin of error from the point estimate to get this interval. So this is the 99% confidence interval for the mean of the population. We could also make our summary statement from the point estimate, margin of error, and confidence level. And a good quick way of saying it would be this. We are 99% confident that the mean of the whole population is approximately 19.7 and that our error is no more than 1.96. Okay, on to the second kind of problem. This problem will involve estimating one proportion. At a city community college, we want to estimate the proportion of students who are studying a natural or a mathematical science. We take a random sample of 50 students. 11 of them are science students, and we'd like 95 and 99% confidence intervals for the proportion of all city community college students who are studying science. Now, the thing that tips us off about the difference between this problem and the one we did earlier about the average weight of adult male bobcats is this. Here, we're taking measurements and then we are computing an average, or you could say a mean, of those measurements from the sample. In a proportion problem, we're not doing that. What we're doing is counting. We count and discover that we have sampled 50 students. We look at the students, we search for the characteristic of whether they are or are not a science student. We find that 11 of the 50 are science students. So with proportions, you're working with counts. With means, you're working with measurements. Here is the formula for confidence intervals for a single mean, and you'll want to remember that p hat means the proportion that we find in the sample, whereas p without the hat means the portion that we find in the whole population. Well, we have most of this information ready to go here. The proportion from the sample is 11 out of 50, or 22%. We're going to want to multiply by the Z critical value. Let's start at the 95% level. That's 1.96. Then we need the square root of this fraction. The easy part is the sample size is 50. P hat goes in next. That's 0.22. And that we multiply by 1 minus 0.22. Clean up our writing a bit. And we are ready to go to the calculator. Now this is a bit of a mess to type into the calculator. I'm going to show you my style. You can do it any way that works. What I like to do is to get this fraction first because it's just a little bit easier for me to see what's going on. So I'm going to have 0.22. I'm going to multiply by 1 minus 0.22. And then I'm going to divide that by 50 and press the enter. That is the number that goes underneath the square root sign. Now once I've got that in the temporary memory of the calculator, it's pretty easy to get the rest of this margin of error. That's 1.96 times the square root of the stuff that I computed just earlier. I press the second key followed by the ants key, and that ants will bring up this value that I had just before. Press press enter there, and that gets me to the margin of error. Well, once we've computed the margin of error, all we need to do is add and subtract it from the point estimate. I've done that already, and there is the confidence interval. This, of course, is a 95% confidence interval for the proportion in the whole population of science students. We're ready now for the last problem. This one is essentially the same as the first problem with one exception. Once again, we have a random sample of 10 adult male bobcats. The average weight of the bobcats in the sample is 19.7 pounds, but this time we don't assume we have a standard deviation from the population. Rather, we have a standard deviation from the sample. The symbol for that is S instead of sigma. Sigma means the standard deviation of the population. S means the standard deviation of the sample. So here's the summary of the information, and the formula for computing a confidence interval when you don't know the standard deviation of the population is this. We're using the t-distribution with n-1 degrees of freedom. Now let me just say quickly that if you are in the part of the course where you haven't yet done confidence intervals for the mean, where you don't have the standard deviation of the population, then you might want to just end the video right here. We're going to be working with a whole different distribution here, and it would be helpful if you knew something about that before you work this problem. So what we're going to do now is look up our t critical value. We have a sample of size 10, so we have 9 degrees of freedom. And we would like the critical value will start out for 95% confidence interval. What we need to do first of all is locate the number of degrees of freedom that we're working with. It's 9 in this case. And then we want to scan across here for our confidence level, 95% confidence level. That tells us that 2.262 is the t critical value that we need here. Once we've got that done, we need to just simply fill in the blanks in the rest of the formula. And now we're going to compute just exactly in the way that we did for the z intervals, or the case where you know sigma rather than s. Let's compute this margin of error first. And I get 1.767. We'll add and subtract that from 19.7. We run these numbers through our calculator, adding and subtracting the margin of error from the point estimate, and we come up with this confidence interval. It's a 95% confidence interval for the mean. Now the instructions were to do this for a 95% confidence interval, which we did right here, and then to do it again for a 90% confidence interval. Well, the 90% confidence interval, just like in the case where you know sigma, is the same. The only difference is going to be in the critical value here, and of course now we're working with the t distribution rather than the z distribution. Keep in mind again, degrees of freedom is 9, and we're going to look for the 90% critical value. So 9 degrees of freedom right across that row. We want 90% confidence. 90% is this column right here. So 1.833 is the critical value. Everything else in the formula is just like it was in the previous step. So we will compute this margin of error, and then we'll add and subtract it to 19.7. Our margin of error comes out to be about 1.3911. So that gives us a confidence interval for the mean of the population, It's the mean weights of adult male bobcats, and we get a range of 18.31 pounds to 21.09 pounds. Last little bit that we might observe here is this. The margin of error is significantly smaller at 90% confidence than it is at 95% confidence. The reason, of course, is that if we want to be more confident, the only way to do that is to allow ourselves a little larger margin of error and therefore a wider interval. If we're willing to be less confident, then we could accept a smaller margin of error and have a narrower or a more precise estimate for the mean. Well, that takes care of the three types. If you are working with one mean where the population's standard deviation is known, then you'll always be using this formula for estimating the mean. It's x bar plus or minus z sigma times sigma over the square root of n. You have to know the standard deviation of the population in order to use that. That's what we did in the first example. If you're trying to estimate a proportion, we use this formula. It's p hat times a z critical value times the square root of p times quantity 1 minus p hat all over n. That is what we did in the second problem. If you are trying to estimate the mean from a sample and you do not know the standard deviation of the population, then you use this formula here. It uses a t critical value, and you need to know that the degrees of freedom are n minus 1, just one less than the sample size. And that's what we did in the third of these problems. These problems together show all of the standard ways of finding a confidence interval for either a mean or a proportion, and if you're working with a mean, for the case where the standard deviation of the population is known and the case where the standard deviation of the population is unknown. There are three and only three cases.